search to find the love within. I came back to let you know, got a thing for you, and I can't let go. My friends wonder what is wrong with me. Well, I'm in a daze from your love, you see. I came back to let you know, got a thing for you, and I can't let go. People go around the world for love, and they may never find what they dream of. What you won't do to do for love, you tried everything, but you don't give up. In my world, only you make me do for love what I would not do. My friends wonder what is wrong with me. Well, I'm in the daze from your love, you see. I came back to let you know, got a thing for you, and I can't let go. Oh, I only want the best, it's true.
That's what I was thinking. Well, it's right at 9 o'clock, so.
Good morning. Okay. So much for that introduction. It's on? Okay. Good morning, everyone. Try that again. Good morning, everyone. Thank you. Yeah, like I said, father was a Lutheran pastor, so you're going to have to deal with that. So, welcome, everyone, to the morning session that we have here for the conference. Again, we're going to go ahead and go through. We have 3 more presentations that we'll have. We'll do a break, and then we'll have our final posters. So we'll have the introductions of all the posters, and then we'll have time for that. And then we have a little bit of time set aside towards the end for sort of an open discussion, so we can talk about stuff for next year, some of the other stuff, maybe if you guys want to talk about things with the FAA and stuff like that as well too. So we'll have a little bit of time, and then we'll break at noon. Just a reminder again, we don't have lunch here, so you're on your own for lunch. There is still some food, though, for breakfast. If you still want to go grab anything, please do help yourself to any of the stuff that's back there. With that, I'm going to go ahead and introduce our next group, which is the Havoc. I think this is with the Space Hardware Club. And again, thank you guys so much for all the work this week. With that, why don't you guys come up?
All right. Well, good morning, everyone. Thank you all for being here. I know I'm excited to be here. I hope everyone had a good drive over. I guess we'll get started. This is Ahac, stands for High Altitude Visual Orientation Control, and it is a rotationally stabilized high-altitude ballooning payload. First things first, I'll introduce myself. My name is Owen Thrasher, and I am the project lead of Ahac.
Hi, I'm Nikki. I am the software sub-team lead of Ahac. Hi, I'm Ainsley, and I'm a mechanical member on Ahac.
And behind me on the graph, you can see all of the rest of our members. We have about 15 in total. We actually might have a 16th joining soon. So we're, medium-sized group here on campus. First things first, just so there's no confusion, I'd like to explain kind of who we are and where we sit within the program that is within the club of SHC. So SHC stands for Space Harbor Club. It is the sort of the largest engineering and science club on campus for undergraduates. Within that general club, there's several programs that deal with things from rockets to rovers to all kinds of things. And for us, we exist within the Balloon Sat program, which is sort of the program that's been holding this conference here, Ahac. And then within that program, we have Ahac itself, which is a project. There are 4 projects in total within Balloon Sat. We all, really excited to work on different stuff. So today, I'd like to tell you about Ahac. I guess the biggest question, the thing we should talk about first is what even is Ahac? Of course, it stands for High Altitude Visual Orientation Control. We put that up at the top. I have heard it referred to as all kinds of things. Probably the funniest is HVAC. But no, it's Ahac. Ideally, we are a high altitude balloon payload we stabilize about the vertical axis. You can see kind of right here, I'll get out of the way here. Here's a 3D mock-up of our 3rd generation model. You can see that we use these lever arms with cold gas pneumatic thrusters on the end. These are convergent, as you can see in the zoom up kind of right there. And it's designed to be able to stabilize to face a certain direction. We've kind of moved into different applications of this technology as of late, but for this particular design that I'm talking about today, this design review, it was designed to capture rotationally stabilized photo and video. As I'm sure y'all know, all of us here launch balloons. Y'all know that once we get up into the stratosphere, you start spinning very quickly. And our goal is basically to not spin. You can see right there's a picture at the bottom. And then we also have our free body diagram. You can see we like to throw that up there in presentations because it gives a very clear overview of what we do. It can sometimes be hard to visualize this. But I do have some video later, so I hope you'll be able to see what we're talking about. And I guess the last thing to note is that we've gone through 4 major iterations or generations. Right now, we just got done with the 4th, and we're still working with that. But today, I'd like to talk to you about the 3rd generation, as you can see down here. With that, we'll go into the specific overview of each subsystem.
All right, so our mechanical subsystem is simple and complicated at the same time. We split it basically into 2 parts, an internal and external structure. The internal structure is where all of the support is going to happen. That's where all of the actual structure is. And we use aluminum threaded rods to make that main support tower with 3D prints to connect them. And then we, of course, have our carbon fiber rod that goes through it just to give us some torque. We also have room in it to have our electrical payload, basically. It's its own little box that just kind of gets slotted in and plugged in. And we also have a little bit of extra room below our tank because when we land going at like 8 meters per second, we kind of want a little bit of crumple zone so that our tanks, which are very expensive, do not break. We also have our external payload, which is mostly for protection from elements up in the atmosphere. We kind of don't want things getting cold, windy, or wet. So we made just a really nice, super light fiberglass composite body. It has some carbon fiber ropes in it just for some more support. And we also have 3D prints to secure it and a little dome on the top for our camera. So that's our mechanical system. Our pneumatic system is also pretty simple. We just have it regulated down twice to get us below 100 psi. And then we go to T, which splits into a counterclockwise and a clockwise rotating solenoid, so we can open and close them for which direction we would like to go. And then those split again to go to each side, and we do make sure to test which side they're on so that we do not end up just stabilizing where we are instead of pushing in the same direction. So our runtime is about 30 to 60 minutes with the amount of nitrogen that we're able to carry. And it's just a pretty simple carbon fiber overwrap tank that we get from paintball stores. So pneumatics is fairly simple, and they're able to use their tubing to figure out where they can sit within the mechanical structure. So they're very flexible.
Yeah, so next we have our electrical. On the left, right, whatever it is, I'm getting all backwards up here, but that's our our 1.0 and 2.0 version, which was on a proto board And then one of our biggest upgrades with Havoc 3.0 was getting our own custom PCB. We have an IMU, a barometer, and a GPS, and the sensor suite allows us to take all of the data that we might need or want on a balloon flight. If we go to the next slide, we can see our software, which is what I mainly work on. We use Arduino C on a Teensy 4.1. One of the main things that we're doing the whole flight is just recording all the data from all the sensors and seeing where we are to know what we should be doing at that point, because we only start stabilizing at about 20 kilometers. So throughout the whole flight, we're just like getting our data at 20 hertz, but once we hit 20 kilometers, we start stabilizing. And in order to stabilize, in Havoc 1.0 and 2.0, we used a very simple bang-bang control system. However, it had a orientation accuracy of about 30 degrees, like plus or minus 30 degrees, which you can imagine is a very large area if you're trying to look. So I came in and upgraded it to a cascaded PID controller, and one of the things is that PID gives a analog output, and as you might imagine, our solenoids and our pneumatic system is a digital on-off system. So we used a custom software implementation of pulse frequency modulation to convert the analog output to a digital output for the solenoids. With this, we were able to get a orientation accuracy of plus or minus 10 degrees and a rotational velocity accuracy of plus or minus 7. So here is Havoc 10, our first true success with this system. And as you can see here, we have our unstabilized, and then we activated at about 19 kilometers. And then you can see it went from completely unstabilized to within our bounds. We have lines for plus or minus 10 degrees there. And then on the next slide, I think there should be our rotational velocity staying between plus and minus 7. So if we move on, we have a video of this flight. Here you can see that it is staying in the same area on the horizon. We will, in the future, have a gimbal system to be able to go to stabilize up and down. Right now we are just working on our vertical, or whatever.
All right, so our new team of Havoc took over during the beginning of 2024. And when we first met in January, we said, we need a goal, we need something to do. And the big thing that was coming up was, of course, the April 8th eclipse. So we decided, you know what, we are going to completely redesign the system and build 2 identical copies in order for the April 8th eclipse. And we're going to fly several test flights before then. So we were able to build 2 payloads, Squall and Whirlwind. They're identical Havoc 3 payloads, and we were able to launch them during the April 8th eclipse. Despite nature trying to take its hold of us, we did manage to launch both payloads with our plus or minus 7 degrees per second and plus or minus 10 degree orientation goals.
All right, so as Ainsley mentioned, we introduced the 3rd generation, why we've made this the goal of Havoc, and she introduced like what the actual mission was. We always try and have some sort of mission, some sort of goal to do per semester or per maybe academic year. And so back, in the first part of 2024, spring of 2024, that goal was to stabilize towards the eclipse. We were able to get our design to be successful, as was shown in the Havoc 10 flight. That was the last test flight before the eclipse flights. I failed to put it up on the slide, so I apologize, but we flew 2 payloads on 2 different balloons, although they were identical. And so those flights were Havoc 11 and Havoc 12. The first payload here, this is Squall. I misspoke there. Unfortunately, as you can see, this is not quite stabilized. It's very random. In fact, this is what we would see if we didn't activate at all. And although we activated, what ended up happening is we did not have secondary retention of our pneumatic tank. Well, when we hit the jet stream, we encountered very, very strong winds pushing us back and forth, and that movement, unfortunately, unscrewed the pneumatics tank and caused it to fall down into the crumple zone that was supposed to protect it in the first place. As a result, although our state machine worked perfectly and the software worked, as well as the electronics, it never staged, it did stage, it never had the propellant to actually do what it wanted to do. So as you can see, it is unfortunately unstabilized. If you hit the next slide. You can also see this with our rotational rate. You can see before that line, sort of the back and forth of the winds, and you can see that that very much continues into our stabilization period, which is rather unfortunate. However, the reason that we flew 2 payloads in the first place was redundancy. You can't really get a harder deadline than an eclipse. It's gonna happen and there's nothing you can do to slow it or move it, right? And so we flew 2 for the purpose of getting that redundancy. Thankfully, the second payload did actually work. This is Warwind, this is the correct one. And as you can see, we were able to stabilize. As soon as we hit stabilization start, we were stabilizing to roughly within plus or minus 10. This isn't as nice, perhaps, as what the original sort of Ahac 10 was, but we would still consider this stabilized. As you can see, we do have a very, very large decrease in the amount of random noise that we have from that left side to the middle to the right. Unfortunately, with this payload, although it worked, it didn't work as long as we wanted it to because it eventually did encounter the same tank decoupling issue because we didn't have secondary retention. But it did it about, we got about 10 good minutes of stabilization before that happened, which would have been enough to see the eclipse. But unfortunately, due to the sort of nature of balloon flights and getting them up in the air, especially in a stressful situation, we got this balloon, which was the second balloon flown, up about 20 minutes later than we meant to. Now, in eclipse, we don't have much time for that totality period. As a result, we did not activate in the totality period. So rather unfortunately, although we did stabilize, the one payload that did see the totality, which was the first one, Squall, did not stabilize at all. The one that did stabilize, unfortunately, did so after the eclipse had already passed. If you hit the next slide. You can also see with our velocity, unfortunately, this was a lot less constrained than we'd have liked it to have been. But we did see some sort of results there. You hit the next one. And now we'll move on to conclusions from these flights.
So a lot of the conclusions had to do with our mechanical system and that retention of the tank. Because it happened twice in both payloads, we were kind of like, okay, that's an actual issue. We were really disappointed that it didn't happen in any of our test flights leading up to the eclipse, because it would have been easy to fix beforehand. But a lot of our the redesigns focused on making sure that that tank was secure, but also still protected from the impact when we land. And also just on trying to reduce weight, because we discovered during the eclipse we were like right at 6 pounds, and that unfortunately made it was quite difficult for us to do some more stuff. Like we couldn't add the gimbal because we didn't have room to add any more weight. So we also redesigned trying to reduce weight and just make a more structured payload that could withstand harder impacts so that we could fly it over and over again much easier, and just make it a little bit easier for us to put together because we were later, and part of that was also just our team's fault because the integration of the payload was not great. It was poorly designed, and so it took quite a while to integrate the payload in the field. So we did a lot of redesigns making sure that we could actually integrate easily. Otherwise, we just basically did upgrades on all the other systems as well to try and keep it nice and secure and overviewed so that it wouldn't have any of the issues that we might have discovered beforehand.
Right. So although it's unfortunate that we did not stabilize during the eclipse and meet our original goal, we learned a lot of things. And there is something I'd like to say. I almost said this in the Meet the Team slide, the second slide after the title slide, but I decided it'd actually be better to say this here. When we did this mission, all of the members on our team were freshmen. Just a year before we flew a payload for the eclipse, most of us had had 0 ballooning experience and minimal engineering experience. And so it was a really, really awesome experience to be able to go do the eclipse. And even if it didn't work, I think the big conclusion here is that, the whole point of STEM and education is to learn and sort of grow our skills as engineers and scientists, technical reviewers, technical writers, what have you. But I think it's important, we took the conclusions from our Ahac 3.0 system, and we designed the Ahac 4.0 system, the fourth generation that I alluded to earlier. As you can see, the mechanical looks very, very different. I mean, the same sort of basic features are there, but you can see we shortened it, we made it a whole lot easier for integration, as Ainsley mentioned, and we also revamped the electrical system as well. One thing that was kind of frustrating in some cases was we had plugs on the boards for our solenoids, LEDs, all the required stuff for a ballooning payload. And the plugs were both on the top side and the bottom side of the board. And then also, because of the way that we did the foam shielding for the Ahac 3.0 system for the electrical board, it was very difficult to sort of wire those threads through. And if you had to replace a wire, it was going to be at least a 15-minute venture. So I'm very proud to say that our electrical team designed a system where we have all of our connectors on one side of the board, and we actually just slide the electronics down into the foam sort of cord right there. And so if we need to replace something, we don't even have to take it out of the foam. But if we do, we literally just it's a chip. You just pick it up and you have it. I think that was really, really awesome. But I think the main thing to take from our conclusions into our future work is that we were able to iterate upon what we had done. And we have taken a lot of, we've learned a lot about what we are doing, just general engineering as well as engineering as it pertains to this specific project. We've talked about the electrical upgrades, we've talked about the mechanical upgrades. We should talk real briefly about the pneumatics upgrades. You can see we have a convergent divergent nozzle. They're still kind of working on that, getting it refined. But as you can see, right there, she's got it. That's allowed us to be a lot more efficient and use our propellant more wisely, because we only have a limited amount, right? But now we can talk about software, which can be kind of hard to visualize, but I think Nikki will do a good job.
Yeah, so after the eclipse, which was very much a use all the old code, put in upgrades, but don't really change it, we went in and said, hey, let's make this really awesome code. So we completely revamped everything using object-oriented principles, and we started using Platform IO and VS Code instead of Arduino C, which has helped us a lot because it's a little more streamlined. And the biggest thing that we have done is just fine-tune the control system that was debuted at the beginning of Ahac 3, and now we are able to get plus or minus 7 degrees of orientation accuracy, which is better, and we are still working on getting that lower. And then on the next slide, we can see our plus or minus 5 degrees of velocity accuracy, which is like getting up to the max there, because that is about how much we can do with the current nozzle design. And here you can see a bunch of pictures. One of the biggest things of Ahac is just taking pictures. It's visual orientation control. We are trying to get these views that you wouldn't be able to get otherwise from a high-altitude ballooning payload.
Thank you. I do want to, and this is completely my fault, completely forgot to put what this flight was. Both of those graphs were from the same flight, of course. That graph was from our most recent flight, Ahac 17. So I suppose it would be 5 flights after the Eclipse flight and 7 flights after that first initial test flight that we had really good results. As you can see, this is a lot cleaner and a lot more refined. And I'm very, very proud of my team for being able to get us to this far. And I will say this flight was, let's see, it was April. No, it was May. It was like May 11th, yeah. It was May. Sorry, we've had so many flights over the past little bit. I'm sure y'all are familiar with that. But yeah, this is our gallery. Although we didn't stabilize, we were still able to get some really awesome images, as was anyone who flew a payload during the eclipse, which I would assume is most of y'all. Raise your hand if you flew or were involved with a team that flew a payload during the eclipse. Yeah, exactly. See, ballooning people, we're all the same, right? We see an eclipse and we're like, yeah, we should do that. So yeah, I'm sure y'all have seen images like this before, but these are the images that we were able to collect. In the top left, you can see this was before the eclipse appeared on the horizon. Top right is going to be as it was appearing on the horizon, and then the bottom two are right during the middle of totality, as we're seeing the curvature of the moon's shadow on the Earth. Just some really awesome images. I'm very, very happy with them. Real quick, do some acknowledgments. Space Hardware Club at University of Alabama Huntsville, that's our sort of core group here. That's what has allowed both this engineering project and many others to work. You have Dr. Gong Wong, who is our faculty advisor, super nice dude. Alabama Space Grant Consortium is a very important one. That's where we get our money, and balloon flights don't happen without money, unfortunately. We also like to thank UAH SWIRL, the Severe Weather Institute for Research and Lightning Laboratories. We launch out of them a lot. And in fact, for those of y'all that were here, was it Wednesday? Y'all saw a balloon launch. And so that kind of operation is actually how we do our test flights. It's very, very cool. And last but not, we also want to thank the original Ahac members, the people who started the project. This project is, I think it's about 6 years old now. And so the current team members, or the original team members have all graduated, but before they left, they gave their knowledge and their base, which was the Ahac 1 and Ahac 2 system, to us to work with. And last but not least, we have the Startup Golf and Country Club, as they were our launch location when we launched out of Illinois for the eclipse. But with that out of the way, thank you so much, ladies and gentlemen, for your time. And do you have any questions that we would like to answer? All right, here in the front.
So what do you guys think is like the limit on the precision for your pneumatic system? Like what is the reason that you're not going to be able to get like significantly beyond where you are right now?
With our current system, we do have a limit where the solenoids in the pneumatics can only be really accurately and safely actuated at around 20 milliseconds, but we have our margin of error because systems are not tested at altitude. So we try to limit that to about 20 hertz, 50 milliseconds actuation time. So with that, we get a set amount of thrust and change in velocity, which is right now about 5 meters per second, or degrees per second, not meters per second, sorry. And having your bounds lower than that minimum thrust really does get you into kind of oscillations within your deadband.
We also, although it looks like with the current solenoids, it's going to be hard to push it any further, we're looking into other methods of control, stuff like maybe bi-level thruster control, other stuff. That's actually a big thing that we're going to do once most of us come back for the fall semester, is we're going to start, the software team and the pneumatics team are going to work together and look at ways to push our stabilization down even further. Over there? I'll let a mechanical person answer that.
So we do have swivels in the line to make sure that there's no forces from the line. So the only forces really acting on the payload are the forces it's providing and the wind acting on it. We do our best to try and keep it as slim as possible so that the wind's not doing too much to it, so that we're not fighting that bad.
Right there.
The bouncing between limits, especially in velocity, it might look very obvious on the graph, but that's really because we're so zoomed in that you can just see it very well. Also, 5 degrees per second is extremely slow for a payload. So even if you're bouncing between -5 and +5 degrees per second, it is extremely, extremely slow.
No, yeah, I completely understand what you're saying. Yeah, in terms of the bouncing as well, a part of that's the deadband, because if we activate within the deadband, we'll start oscillations, especially with the PID system. But yeah, to answer that question, we use 1 meter long carbon fiber rods, and we use that. We're looking, actually, one of the ways that we're looking at getting better control is by shortening those rods so that we have less sort of rotational torque on the system. The reason it's 1 meter, quite frankly, is because that's what's available. That's what we get from McMaster-Carr. Getting a smaller size is more expensive and a little more difficult. We could cut them, and that's something we're looking at, but cutting carbon fiber is a little bit difficult and carries some safety risks. But we're looking into it. There's ways to do it safely. I mean, people do that.
You have to mount your thrusters on the ends of the rods, and you can't just mount it on top or below. And then in theory, you could have a course set at the all the way out, and then bring it in and have once you've taken most of the initial rotation off, make it fine.
Yeah, of course. That is completely possible. In fact, the way that we do our nozzle holders, it's just the nozzles are on the side, and there's a hole in the middle where the carbon fiber rod goes through. So if we literally could just 3D print that section and sort of push it in. And that is something we're actually looking at and that's why I mentioned bi-level thruster control is like we're looking at maybe having a sort of set a thrust profile, I suppose, for when we're trying, like if we're facing the complete wrong direction, if I'm facing the wrong way, I want pretty much maximum power to get myself to face what I want to face. But maybe if I'm like this far away, I just need just a little pulse to push me. So that is something that we're looking into, and that's a very valid point. For this system, again, this was the 3.0 system, so it was our first iteration. It's the third iteration, but iterations 1 and 2 were done by the old Ahac team, the people who have all graduated. So 3.0 was I probably should mention that earlier, that was our first iteration for us. So that's why I was saying in the conclusions is we learned a lot about what to do, especially what not to do. And so from that, we have now designed 4.0, and even as we come back to the next, this fall semester, we're gonna make it hopefully even better. But yes, that's a very good point. Any other questions?
It's about, okay, it varies depending on how frazzled we are putting it together. But it's about 5.6, 5.7 pounds now. So we have a little bit of wiggle room now. And we're hoping to get it down even further as we continue to work with better materials.
And just a very small thing to add to that. We haven't been terribly concerned about weight for this past sort of semester because I said earlier we're moving into different kind of areas of looking at this research and applications. We actually are acting as a ride share for a research group in Huntsville that's testing out, they want to test out filters on cameras and high altitude to do atmospheric stuff. I'm not an atmospheric major, so I apologize. But they needed to be rotationally stabilized. And so their payload alone was 2.5 pounds. So we got our payload to be as light as possible. But normally we try and do FAA 101 exempt flights so that we don't have to bother with stuff. For these flights, though, we ended up doing FAA 101 compliant. So we did all the stuff like the radar reflector, we did the paperwork, we contacted the FAA. We went through all of those hoops that we wouldn't normally do, but we did recently, and that's why we haven't been terribly concerned about the weight for this sort of past cycle. Thank you for your question.
Yes, it is. We have our GitHub repo. I think it's just called Ahac Balloon, and Drew can show you it. He has it up on his computer right now.
I just wanted to make a comment that years ago we had a balloon set class at the UAH for senior design, and it was stabilization. And the concepts that were done was ducted fans on poles, a reaction wheel mechanism, which was a little heavy, but it worked. We kept it under 6 pounds. And
been told that if you want any food, now is your time. And they're going to start cleaning up here in just a couple minutes. So if you want to go get something real quick, do it now. Got you up on the screen. Oh, here's a laser pointer if you want it. Oh, you got one? Okay, we'll just leave this one up here then. So we have our next talk up, testing low-cost Geiger counters for potential use on stratospheric ballooning missions. With that, you can go ahead and get started. Thank you.
Thank you for the introduction. Testing. Hello. Okay. So my name is Joseph Shin. I am with the University of Minnesota Twin Cities and the Minnesota Space Grant Stratospheric Ballooning Team. And our research that we did that I will be presenting is testing low-cost Geiger counters with the potential use on stratospheric ballooning missions. So some background that I should first cover is what is a Geiger counter and how do they work. So Geiger counters, also called Geiger-Müller counters, are sensors that detect ionizing radiation. They do this by using Geiger tubes, which are tubes that detect the ionizing radiation passing through them, and when the ionizing radiation passes through, it ionizes the gas and produces a signal output. We can use this electrical pulse to count the radiation rate, typically in counts per time interval, and these devices have been historically used in high-altitude ballooning cosmic studies since the early 20th century. And there are many different types of Geiger counters, as you will see in this presentation, such as Geiger counters with pancake versus cylindrical tubes, Geiger counters with different pulse interfaces, and internal and external logging devices. Some more background that I will cover will be on cosmic radiation. So cosmic rays are high-energy particles from space. They are usually particles from supernova remnants and other galaxies. And when the cosmic radiation enters our atmosphere, you can find the most radiation about 60 to 70,000 feet in the air. This is called the Wegener-Pfotzer maximum, also called the RP max. This is because when primary cosmic rays hit the atmosphere, which are mostly protons, they scatter and shower secondary particles. So above the RP max, there are fewer primary interactions with the atmosphere, so there is lower secondary radiation. And below the RP max, there is a lot of attenuation and decay of secondary particles because of the denser atmosphere, which is why we see the maximum at the RP max. Another concept is the Forbush decrease, which is a dip in cosmic rays due to solar magnetic activity. This is when CMEs push cosmic rays from outside our solar system away from the Earth. So the motivation of why we looked into low-cost Geiger counters is because our ballooning team has historically used three older devices. They're called the ARM-60, ARM-80, and the Nulog Geiger counter. And these units, they are old and they won't last forever, so we need cost-effective replacements that will be able to handle the conditions of the upper atmosphere. Also, this year is the year where the peak of the sun's 11-year activity cycle occurs, and during this period, it's the period where the sun experiences increased solar flares and CMEs, which previously mentioned can push cosmic rays away. So our research question was, which new-to-us Geiger counters are viable to characterize cosmic radiation on stratospheric ballooning missions? So before I cover the new Geiger counters, I should probably go through the specs of the old ones that we have historically used. So we can see the ARM-60 on the left, the ARM-80, and then the Nulog 247. So these are relatively expensive compared to the ones that we just recently purchased. They also have small size and small mass. The two RM units produced by Aware Electronics, they have external logging capabilities, which mean that We can connect it to our paddle flight computers or other flight computers that we use and log alongside other flight data such as altitude, GPS, temperature, while the new log Geiger counter independently logs radiation data. And out of the three, in my experience and our team's experience, reliable of the three, while the other two have some slightly small issues. They're prone to damage or they fail in low pressure. So our criteria for our Geiger counter, new Geiger counter selection are these four: environmental robustness, so they should be able to handle the cold temperatures, low pressures, and other conditions of the high altitude conditions. They should have a sufficient count rate. So counters need to be able to register hundreds of ionizing events at rates of hundreds of counts per minute. Some of the Geiger counters we purchased on the website claimed that they only had a maximum counting rate of 20 counts per minute, but we found that claim to be untrue. Another selection criteria that we looked at is portability and integration. So we wanted the new Geiger counters to be small enough and light enough to put into payloads. And the last criteria is microcontroller compatibility. So we preferred and wanted to find Geiger counters that we could connect to our existing flight computers so we can log the radiation data alongside the flight data that we collect on those computers. So these are the four new to us Geiger counters that we evaluated this year. So on the left, we see the gravity Geiger counter. This is the cheapest out of the four. We also looked at the Mighty Ohm, Shkalacar, and GMC 500 Plus units. They are all relatively small, and the three on your left here show that or have external logging capabilities. So we can connect them to our flight computers, some of which require modifications such as the Mighty Ohm and Shkalacar units. And then the GMC 500 Plus has its own internal logging method as well. And for power, the Gravity and Shkalacar have or receive their power from our flight computers, while the Mighty Ohm and the GMC 500 Plus units have their own internal batteries. So most of the counters that we got in the previous slide required external logging. So we used the paddle flight computer. And the paddle flight computer uses the Arduino Nano 33BLE microcontroller sensor suite. So this microcontroller and the entire flight computer can log all sorts of flight data that we can plot alongside our radiation data. On the other hand, the GMC 500 Plus unit, it's a self-contained Geiger counter. So it has, excuse me, it is self-contained, so it has its own battery and logging, like mentioned before. So regarding the external logging modifications, some of the Geiger counters needed new soldering, so we had to solder a lead into the circuit board of the Geiger counter, where the voltage cleanly changes to count radiation hits. And then we took that signal and then used that signal to count the radiation hits over the time interval of the paddle, which is about 6 seconds. We also added a heating mesh specifically for the Shkalacar unit because it was very temperature sensitive, especially to cold. And we also added power extension to the Mighty Ohm unit, and we had to make modifications to the code for the Arduino. So in total, we did a total of 4 flights this year from January, March, April, and May. Many of these were successful, and as you can see on the right, this is a picture of our stack that we sent up in March, which contained all 5 of our Geiger counters. So for our results, the first result up here is the RM60, the unit that we have historically used. So we decided to fly this on the first 2 of our flights to see and make this a baseline and compare the results from this unit, which is reliable, to the new Geiger counters that we tested. And we can see on the left axis is altitude, and then the right axis is counts every 6 seconds. So the blue line is altitude, and the red scattered plots is the RM60 hits. And we can see that there is a curve as altitude increases until it stops at around 60 to 70,000 feet, which mentioned before is the Wegener-Pfotzer maximum. And then we can also see the dip in radiation after that altitude, and then we reach peak at 70,000 feet for radiation again during descent. This graph looks very similar to the previous graph. This is for the gravity Geiger counter unit that we tested. This has a more higher count rate than the RM60. So the RM60 peaked at about 30 counts every 6 seconds, while this unit had a maximum count rate at the Wegener-Pfotzer maximum at about 100 counts every 6 seconds. And you can see that there is a more cleaner, thinner defined radiation curve, as well as a more defined Wegener-Pfotzer maximum. This unit was also very easy to integrate with the paddle 33, just like the RM60. And finally, for our top performing counters, we have the GMC 500 Plus. So here we have two figures. So the top figure is from March. This was a regular flight, and then the second flight was from April. Our Geiger counter payload in April was attached to a vent, and the vent only went up to about 40,000 feet, which is why the shape of the radiation curve is different. So we had two of these Geiger counter GMC 500 Plus units. So we decided to see if orienting the Geiger tubes in the units had an effect. So the blue line is unit A in both graphs, and the red line is unit B. And in the first flight, we oriented the Geiger tube of unit A horizontally, and then unit B vertically, and then we swapped it in the second April flight. And we can see that unit A seems to be better at counting and therefore more sensitive in both graphs. So we did another experiment later to test the orientation only using one Geiger counter on a servo. Oh, correct, unit B. We also had two slightly underperforming counters. So first is the Mighty Ohm Geiger counter. So this was the first flight that we flew this year. And the Mighty Ohm Geiger counter does have the beginning of the RP maximum visible in its radiation curve, and it looked promising, but however, it stopped logging after about 110 minutes into flight. We believe it was because of the two internal AAA batteries that didn't provide enough battery life for the entire flight. So later on, we made modifications to extend the battery life by soldering new battery connections so we could have 4 AA batteries. However, we stopped trying to work on it after 2 more flights because it didn't produce any usable or readable data. And finally, from the 4 new Geiger counters, the Skala-Kar Geiger counter we flew multiple times. So the first time we flew it in March, which is the top figure, the cyan line is the internal temperature of the payload, which is collected from the Paddle 33 flight computer. We can see that whenever the temperature dipped below 24 degrees Fahrenheit inside the payload, the Skala-Kar Geiger counter unit would start slowing or decreasing the count units all the way to 0. And then when the temperature would increase back up above 24 degrees Fahrenheit, it would start counting again normally. So in the next flight, we decided to add a heating mesh to the Geiger counter, and that is the bottom payload. And we also decided to use a more insulated payload box. And, and as we can see, the internal temperature of the May flight was above 24 degrees Fahrenheit the entire time, and it was able to successfully produce a graph with a radiation curve. Overall, it was pretty disappointing because it was very temperature sensitive, even in modest cold. So this is another side experiment that we did in this research. So we decided to test an ARM 80 and GMC 500 plus Geiger counters regarding orientation. So cosmic rays come in all directions towards the Earth. And when you're up in the atmosphere, there's more atmosphere sideways than up. This suggests that there is more vertically oriented cosmic radiation that penetrates through because of the lesser penetration depth from the cosmic rays above. And we want to investigate how efficient it is to change the Geiger tube orientation and to see if the greater top-down surface area had an effect on radiation count rate. So we can see here, so the ARM 80 has a pancake Geiger counter or Geiger tube shape. So when it's vertical, when the axis of the Geiger counter is vertical, we should presumably see more counts, while the horizontal orientation of the GMC 500 Plus's Geiger tube should have the higher counts, which is what we expected. However, we can see that the results were slightly different than what we expected. So the ARM 80 mentioned earlier is historically used, and we chose it for the servo experiment because we thought the orientation would have the biggest effect because of its large Geiger tube geometry shaped like a pancake. Each orientation in the servo, I should mention, is held for 1 minute by the servo and then switched, so from vertical to horizontal in this case. And then the blue indicates in these figures the horizontal axis orientation, while the red indicates the vertical axis orientation. So we can see from these figures that orientation had some subtle effect, which is opposite of what we expected. In graph B, during ascent, the horizontal count rates were higher. We expected vertical to be higher because of what I mentioned earlier. And in figure C, we can see that visually see that there's no effect of orientation, which is expected because we are at the Wegener-Pfatzer maximum. And we also did the orientation testing on the GMC 500 Plus Geiger counter. So we followed up with the GMC 500 Plus because of our earlier experiment with 2 different detectors in different orientations, but we found that one was more sensitive. So we decided to make a cleaner experiment by only using one on the servo system. And as we can see in the zoomed in figures from B and C, there wasn't really much of an orientation effect at all. So in conclusion, going back to the low-cost Geiger counters, we found that the most suitable Geiger counter replacements are the DF Robot Gravity and the GMC 500 Plus Geiger counters seen on the right. Both had very defined radiation curve data, and its Wegener-Pfatzer maximum was visible. And they are both very affordable and accessible alternatives compared to our discontinued sensors like the ARM60. And we also concluded from what we have seen so far that there is not much of an orientation effect. So we advise that it is best to mount your Geiger counters or other radiation sensors in the same orientation every flight. Future work, so we want to continue further orientation testing on Geiger counters, specifically orientation testing across different tube geometries and sizes. I think it would be important to see how big the Geiger tube sizes actually are and compare it and see if orientation does have effect on them in future flights. We also want to capture radiation changes during the Forbush decreases during events like CMEs. And we also want to integrate the GMC 500 Plus unit, which has internal logging. So we want to change it so it can be used with flight computers and do external logging. So we already did that with a Piccolo flight computer, which there was a presentation on yesterday. And we want to try and integrate it with the paddle and pterodactyl flight computers as well. And we also want to also look closely at the external and internal log for the GMC 500 plus unit when we do that. So some acknowledgements I'd like to make. So I'd like to thank the University of Minnesota Stratospheric Ballooning team for their support, especially Dr. James Flotton, our advisor, and some other members like Daniel and others for support during flights. I'd also like to thank the NASA's Minnesota Space Grant Consortium for their funding and support, as well as input from other ballooning teams participating in the Solar Max initiative, such as because they recommended Geiger counters like the GMC 500 plus. These are the references from my manuscript, and if you can, please go read it. And that is the end of my presentation, so I'll answer any questions if you guys have any. Thank you. That's a good question. So in the settings, you can change it in the GMC 500 plus Geiger counter. So there is the setting for CPS, counts per second. When you do that and export the data from the Geiger counter, you see CPS and CPM. So it can do both counts per second and counts per minute.
Well, what I'm wondering is if you're comparing apples to apples here, because the longer the time that you integrate over, the less noise you're going to have. And it seemed like when you were applying the GMC 500, it had actually fewer data points. It had a bigger time interval between data points. But if you go to your other two and integrate over the same time interval, you would bring your noise down.
That's correct. I believe the graphs that we used, I can go back here, is counts per minute for the GMC 500 plus units. So I think we could, in the future, we can also compare it with counts per every 6 seconds to see the differences between all the different Geiger counters.
Or average the other ones over longer time.
Correct.
Well, I was going to say, you don't have to do it again. You have the data. You can just take 10 of your 6-second intervals, and you just add them together, and that's the number of counts you had in a minute, right? Because you have 6 seconds. But the other thing you want to be careful, since you said there's a setting for counts per second, you want to be careful that's not just changing the units, and what you really care about is how long of a time bin you are counting over. So, because that's what's going to determine your statistical fluctuation. You can always convert the units to different, you can convert the minutes to seconds and you can make them comparable. But what you really want to know is how long of each time you get a new set of counts, how long you're counting over.
Yeah.
For the audio, why didn't you power it directly instead of
So I believe back in January we tested that, but for some reason it wouldn't power through our Paddle 33 flight computer at the time.
Okay. Any other questions? Eric?
already addressed just being editor or whatever. I'm just remembering reviewer comments as well. This was already kind of addressed, but I would highly suggest from the reviewer comments that came in, and it's been addressed in them all already, but it probably would behoove to try to do some statistical averaging per minute because that's typically what's been done historically. So that was kind of some of the reviewer comments that came in too. So if you want to, especially those every 6-second data plots, if you could kind of do per minute, kind of just after the error bars, would be tougher. So that was kind of what we into. Again, I have the advantage of seeing reviewer comments, so if you guys can do that, great.
For sure.
Okay. Any other questions? If not, let's move to our next speaker and give another round of applause. Okay. Next up, we have Taylor University with investigating stabilization in lower stratospheric temperature and atmospheric gravity waves during the April total solar eclipse. Actually, yeah. If you want to put on thumb drive, then I'll.
Yeah, let me go grab that.
Okay.
Yeah, we could, here. Plug this one in, just the PowerPoint version.
Now we're going to go ahead and get started. So, Ian, if you want to go ahead and get started, and we'll go from there. Thanks.
Great. Hey guys, glad to be here today. Thank you for joining me. My name is Ian Otis, and I am a undergraduate junior at Taylor University studying data science. And today I'm going to be presenting our research that was consisting of a team of myself and my fellow researchers from Taylor University, Dr. Fola Ayano, Dr. Amish Mishra, Ethan Elliott, Charlie Michaels, and Ethan Sosnowski. And today I'll be presenting our study entitled Investigating Stabilization in Lower Stratospheric Temperature and Atmospheric Gravity Waves during the April 8th, 2024 total solar eclipse. This research focused on analyzing high-altitude weather balloon data to uncover how solar eclipses may influence the dynamics of the stratosphere. Perfect. So today I will briefly introduce the topic, explain the motivation behind our study, walk you through our methodology, and then discuss our findings. So firstly, what are atmospheric gravity waves? Well, atmospheric gravity waves are vertical oscillations in the atmosphere that occur when air is displaced vertically and gravity acts to restore it. So I'll throw up a visualization here. So these atmospheric gravity waves are commonly triggered by factors such as mountain ranges or by strong weather events such as thunderstorms. So in the case of a mountain range like that is depicted up here, when air is forced upwards, it cools, and then gravity then acts to pull it down to restore balance, which then causes the air to warm again, which subsequently causes it to rise. And this oscillation carries energy and momentum vertically, sometimes across vast altitude ranges.
and gradually dissipates as equilibrium is restored. There we go. Although invisible to the eye, atmospheric gravity waves play a vital role in the functioning of our atmosphere. They help regulate atmospheric circulation, influence weather patterns, and contribute to the stratospheric temperature structure. They also affect aviation, satellite trajectories, and weather forecast accuracy. So just a few reasons why studying atmospheric gravity waves are so important. But here's where it gets especially interesting. While most atmospheric gravity waves are generated by familiar mechanisms, it has long been hypothesized that solar eclipses, with their sudden dramatic cooling, could also serve as a unique natural trigger for atmospheric gravity waves. During a total solar eclipse, the moon blocks incoming solar radiation, causing a rapid and localized drop in temperature in the atmosphere. This kind of fast, large-scale radiative forcing is almost impossible to replicate under normal conditions. These brief windows offer a rare scientific opportunity, a high-speed natural experiment in atmospheric dynamics. Earlier studies, including the 2017 and 2023 eclipses, hinted at both atmospheric stabilization and gravity wave formation, but the evidence remains incomplete, and many questions are still left unanswered. So that's what makes this line of research both timely and important. By better understanding how atmosphere reacts to sudden changes in solar radiation, we can refine climate models, improve forecasts, and gain deeper insight into the complex interplay between radiation and atmospheric motion. So our research was guided by two central questions. Firstly, does a total solar eclipse stabilize lower stratospheric temperature? And secondly, can we detect the presence of atmospheric gravity waves in high-altitude balloon data during and after the eclipse? So to answer these questions, we designed our experiment using data collected during the April 8th, 2024 total solar eclipse and focused on temperature variance and spectral analysis techniques to observe potential wave activity. So near space launch and near space education. Companies in Upland, Indiana that make satellites for NASA, the Department of Defense, and several Fortune 100 companies launched a total of 14 high-altitude weather balloons across Indiana on April 8th, 2024, both before and during the total solar eclipse. These balloons were equipped with a variety of sensors that collected temperature, acceleration, light, infrared and ultraviolet radiation, global positioning system coordinates, altitude, and more. Specifically, measurements of temperature, acceleration, and light were recorded every 2 seconds over 20-second intervals. Other measurements were collected once at the end of every 20-second interval, and this data was exported into a packet. So from the full data set, we selected 5 balloons that had the most intact and high-resolution data for our analysis. 2 of these balloons were launched at Indianapolis Motor Speedway. One was launched before and collected data before the eclipse began, and one was launched during and collected data during the total solar eclipse. And I will refer to these as IMS pre and IMS during, respectively. 2 more balloons were launched at Upland, Indiana. One at Taylor University, which I will refer to as Eastbrook, and one at Near Space Education, which I will refer to as NSE Upland. And lastly, our 5th balloon was launched in Monroeville, Indiana, and I will refer to this one as PFW EDU. So a key comparison in our analysis was between that IMS pre and IMS during balloon, as we had a control balloon that was able to collect atmospheric data before the eclipse, and then one that collected during the eclipse from that same launch location. So to begin with our temperature stabilization analysis, to assess whether the eclipse stabilized stratospheric temperature, we compared the temperature variance from our IMS pre and IMS during balloons. These balloons had nearly identical altitudes, launch locations, and flight durations, which are ideal conditions for a controlled comparison. The main difference was the time of data collection relative to the eclipse's totality. We focused on data collected above 12 kilometers, which helps us correspond to altitude ranges in the lower stratosphere, as it ranges from roughly 12 kilometers up to about 25 kilometers. So we focused on data that was collected within this altitude range for our analysis. Within this subset, both balloons exhibited similar flight durations in this altitude. IMS during for about 40 minutes and IMS pre for about 36 minutes. We used Levin's tests for equality of variances and calculated the actual temperature variances to evaluate the eclipse's impact. So the results showed a clear and significant reduction in temperature variance during the eclipse. IMS pre had a much higher variance than IMS during. Specifically, the p-value from Levin's test was 6.466 times 10 raised to the power of negative 19, confirming a statistically significant difference. Also, when directly comparing the temperature variance figures for these balloons, IMS pre was found to have over twice the variance of IMS during. We then expanded our analysis by looking at our 3 additional balloons, Eastbrook, NSC Upland, and PFW EDU, all that were launched during the eclipse. Each of these balloons also showed a low temperature variance in the lower stratosphere. The consistency that we discovered helped to support the idea that eclipse conditions stabilize the atmospheric temperature, specifically in the lower stratosphere, across multiple locations. So based on our lower stratospheric temperature analysis, we concluded that the eclipse exerted a stabilizing effect on lower stratospheric temperature. The sudden reduction in solar radiation during the eclipse could have suppressed temperature fluctuations in the stratosphere. Since the stratosphere lacks a strong vertical convection, the loss of solar heating may have caused the atmosphere to reach a temporary equilibrium, reducing fluctuations in temperature. And this result aligns with theoretical expectations and expands on findings from prior eclipse-related research. So in addition to our temperature stabilization analysis, we also investigated whether atmospheric gravity waves were generated during or after the eclipse. To do this, we used 2 common signal analysis techniques for atmospheric gravity wave detection: the fast Fourier transform and the continuous wavelet transform. So the fast Fourier transform identifies atmospheric gravity waves by converting time-based data, like wind or temperature, into the frequency domain to reveal dominant oscillation patterns or periodic signals. Peaks in this resulting spectrum would indicate gravity wave activity at specific frequencies that are characteristic of atmospheric gravity waves, allowing us to detect and quantify their presence. Secondly, the continuous wavelet transform identifies atmospheric gravity waves by revealing how different frequency components evolve over time within a signal. Unlike the fast Fourier transform, it captures both the frequency and the timing of transient wave activity, making it ideal for detecting time-localized atmospheric gravity waves. We decided to use interpolated wind speeds, calculated from our latitude and longitude coordinates, as well as temperature data that was recorded by balloons that were above 12 kilometers. So to begin with our fast Fourier transform results, this analysis of our IMS during balloon showed promising results. We observed strong frequency peaks in the 0.001 to 0.002 hertz range. And these specific frequencies fall within the expected range for atmospheric gravity waves in the stratosphere. Importantly, these peaks were present in both temperature and wind speed data. So to determine the coherence between these 2 data sets, we also computed the coherence spectrum between IMS during's temperature and wind speed and found a correlation value of 0.64 at these frequencies. This moderate level of coherence can support the interpretation of a gravity wave affecting both variables simultaneously. Let's see here if I can point that out. So as you can see, right around the 0.001 to 0.002, we notice a couple of peaks there, as well with the corresponding coherence, just to point those out for you. So to complement our fast Fourier transform results, we used a complex Morley wavelet for our continuous wavelet transformation. The wavelet analysis revealed a strong localized signal at around 0.00125 hertz, appearing shortly after third contact when the eclipse's totality ended in our IMS during data. And this is visualized by the horizontal bar in the scalegram enclosed in the red box. You can kind of see a horizontal bar in that area, and that scale right around 800 corresponds to that 0.00125 hertz frequency. So a horizontal bar such as this one at a frequency range that is consistent with our fast Fourier transform findings can be an indicator of atmospheric gravity wave activity. So to reflect on both our gravity wave findings, both our fast Fourier transform and wavelet analyses point to atmospheric gravity wave activity shortly after the eclipse's totality. The frequencies that we detected that were centered around 0.001 to 0.002 hertz fall within the established range for atmospheric gravity waves in the lower stratosphere. Additionally, the presence of coherence between wind and temperature data that we found in our IMS during data at these frequencies is also telling. While noise can create apparent peaks, coherence suggests that these signals are physically related and behaving in a wave-like manner. But what's especially important is the timing. The strongest wavelet signal occurred just after third contact, right as the atmosphere begins rapidly reheating. And this matches observations made in previous solar eclipses, such as the 2017 eclipse using GPS tech data by Ahac and Yajit. So our results don't just stand alone, they extend and reinforce a growing body of evidence that eclipses can generate atmospheric gravity waves, likely due to the abrupt changes in solar forcing. This adds confidence to both our methods and our interpretations of our results. So the combination of our fast Fourier transform and our wavelet results suggests an atmospheric gravity wave may have been generated immediately following the eclipse's totality. While more data is needed to confirm this definitively, especially from a broader network of observations, our findings are a strong indicator of atmospheric gravity wave activity during this unique atmospheric event. So to build on this research, we propose a few improvements that would help future eclipse observations. Firstly, we recommend launching balloons earlier and recovering them later to capture a larger atmospheric time window. This would improve our ability to isolate eclipse-specific effects from background variation. Additionally, sampling data at 1 second intervals rather than 2 would help us to increase our temporal resolution. Additionally, improved signal processing, spatial coverage, and phase analysis could enhance the detection of gravity waves in future eclipse events. This work would not have been possible without the support of the Indiana Space Grant Consortium and the contributions of Near Space Launch and Near Space Education. We also thank Taylor University interns Hannah Peffley, Christine Lee, and Nigel Megason, whose efforts in data cleaning and preparation were essential for our analysis. Thank you all so much. Does anyone have any questions? Yes.
Go back to your last graph.
Yeah, of course. Oh, wait. This one here?
Right, so I'm just looking at your time axis.
Yes.
It looks like that box lasts for about 12 seconds. Is that true?
No, sorry. No, sorry, this is
12 minutes.
This is minutes, I believe. Yeah, sorry, I think I did not update this from the manuscript that has been updated. But yes, this is, the 8 is April 8th. And then it would be 3 p.m. Eastern Daylight Time, which I should have included the UTC minus 400, but that is included in the manuscript and is detailed a little more specifically. But no, the eclipse's totality in IMS during was around 3:09 p.m. to 3:11 p.m. Eastern Daylight Time. And so that would be right about here, which is kind of where we see this horizontal bar beginning, which then lasts for upwards of about 20 minutes. So, yes.
Just a follow-on, that is, you had light sensors. Does that mean that you were able to compensate for the fact that third contact is different if you're on the ground, or if you're in the air, or with the different balloons spread around the state? Did you adjust third contact timing for every balloon?
Good question. Yes, so we did. So part of the data set that we had received was a secondhand data set. So Near Space Launch and Near Space Education had collected the data, and then a prior research team had worked with data handling and data cleaning. And as part of that, they calculated, I'm not sure exactly using what sensors, but with the eclipse's path at every data point, what percentage of totality each balloon was experiencing at the specific 2-second timestamp. And so from that data, we were able to determine when complete totality ended, which would mark the beginning of third contact. So that was already data present in our data set. So our research team this semester did not have a part in determining how that was calculated. All I know is that that was calculated before we received the data set. Yes?
Related to that, thank you, Jan, for stating that. So make sure that that's outlined in your manuscript, because that was one of the things, again, reviewer, you got my.
Yes, definitely.
Sending to me as editor, that was one of the things that I think had also come through, is trying to clarify that. And
Yes.
the Eastern time is also critical. So
Yes, that was all.
make sure that it's under control. And then maybe not just for you, but resolution as far as temperature, 1 second resolution, it might be off, whatever. I don't know that 1 second resolution on temperature may be as critical as maybe for your wind data might be more critical.
Right.
I don't think temperature data much more than 2 seconds is going to probably make that big of a difference. We can go offline to other people, whatever, but I don't think temperature is going to be as critical as maybe your other parameters.
Gotcha.
Comments more than anything, just keep those in mind.
Perfect. Yes. No. Of the Eastern Daylight Time, all that times and stuff has been reflected in our manuscript. So when you guys definitely encourage you to take a look at that, as that will have just a lot more detail on our analysis. So super excited about that. And yes, I believe part of our suggestions were more focused on the wind speed resolution as well. So great comments. I appreciate that.
Any other questions? If not, let's give them another round of applause. Okay, we're not doing bad on time. I know Eric wants to do an announcement. I think Bill also wants to do an announcement as well too. So I think we'll do a couple announcements, and then we have our poster session at 10:30. So I think we're just going to kind of just jump into that poster session. We'll have the poster presenters do their quick elevator pitch on those. So yeah, Eric, did you want to, or Bill? Okay, so Bill, if you want to.
Just a quick show of hands, how many of you would like to meet somewhere for lunch afterwards, and how many have to leave? Who would be interested in meeting somewhere for lunch after the conference? Okay. Chinese food okay? Okay. 88 Buffet, it's on University Drive, about 1.5 miles from here. So it's called 88 Buffet. And the other thing is, the people that were looking at, that attended the Pico Balloon workshop, I do have the Tracheto boards for those of you who did not get one. Come see me up at the table up there in the back, and I'll hand you your kits.
Thank you, Bill. Okay, and Eric? Do I need to do a recovery?
Yeah, I wanted to mention the Pico balloon we did for the workshop on Tuesday went to Iowa. So I balloon mailed it to Iowa, and it hit a severe thunderstorm near Des Moines and came down in the farmlands of Iowa. So I'm giving a challenge to Matthew and his Iowa team to go get the payload from the workshop.
I have a plane, so yes, we'll make that attempt. So, okay,
Let's take 5 quick. Let's have folks take a break.
okay.
PDF,
So
Adobe just crashed on me, so I get to. So.
again, that seems to be the theme. Technology has been not our friend today. We'll just take a quick 5-minute break, and then Eric will come back. So, you need to use the restroom, grab something to drink or something like that. Do so, and then we'll come back.
So this is not part of the poster session, but on the first day, we were talking about who wanted to talk about what, and we're still here. One of my students, Majid, actually is interested in showing people his 360 VR goggles, if anybody wants to. It's not part of the poster session, but he is set up in the back if anybody wants to see some very cool 360 video using goggles. Good. I got the 2 PowerPoints. Good. Oh. Okay, I'll start with the PDFs and then the PowerPoints if they don't show. Then those. All right,
I said 5 minutes and it's already been 5 minutes. So let's kind of do the following. So what I would plan to have done, I've got 2 PDFs and 2 PowerPoints. And so if I can have the camera limits folks ready to go here to give their speech, and then University of Minnesota Cosmic Ray folks. And then at Moses, I don't see the poster, but we had the talk yesterday. That's also a poster, and then I also have a poster, and so I will wrap up with myself. But let's have Chestnut Hill start off with kind of giving you their 1-minute spiel first. So take it away.
Good morning. I'm Jude.
And I'm Mariana.
And we're from Springside Chestnut Hill Academy, and our project investigates the feasibility of using Insta360 X3, which is a consumer-grade 360-degree action camera, to record and capture continuous footage of high-altitude balloon launches with limited battery life and reduced atmospheric conditions and turbulence. And we ran a multitude of different ground tests and field tests, and along the way captured a bunch of different interesting pictures, like the burst shot up on the screen. If you're interested, come stop by our poster.
Thank you for that. And then next, University of Minnesota, Cosmic Rave.
Hi, my name is Monica Robles, and I developed a cloud chamber to investigate cosmic rays. For those who don't know, a cloud chamber essentially allows for visualizing the trajectory of radiation within a supersaturated vapor. Once the radiation interacts with the vapor, droplets are ionized, and you can see the trails that they leave behind, particles leave behind as they enter the supersaturated vapor. We got a lot of cool footage and a lot of cool data, so if you guys want to stop by and check out my poster over there, I'd really appreciate it. Thank you.
Thank you for that. And then we're going to be switching over because the next 2 I've got here are on PowerPoint instead. So, at Moses. Yep.
Hey everybody, you've all seen this at this point, but I'll be postering, I guess. I'll just kind of be standing around if anybody wants to talk a little bit more about Atmosis, what you can do with mission predictions, but also just talking about how in the commercial scene we can help out with what everybody here is doing with college programs and high school programs. We'd love to be more involved in some of the stuff you're doing. So come by, say hi, and let us know what you're doing and if there's anything that we can do to help.
Great. And then myself, Eric Agamson from St. Catherine University. My poster is just sort of kind of a conglomeration of a lot of things. So it's using my high-altitude balloon trailer, and so there's sort of a pun here for those of you that live in the state of Minnesota. So there's this advertisement on KFAN that's about our football stadium. The stories a stadium can tell. I borrowed that theme, and so it's now the stories a high-altitude balloon trailer can tell. So anyhow, it's kind of using our high-altitude balloon trailer as sort of a means, just kind of wanting to talk about sort of the modifications that we've made to it since we bought it, some of the capabilities it has, and then using that as a means to sort of talk about some of the thermal wake research that we did in 2017, and then some of the work we did with NABP, some of my alumni did for temperature research, and then I'm also willing to talk about Geiger research as well. I don't have much of that on this poster, but willing to talk about that as well. And talk about my balloon trailer and some of the events that happened during that, and the 12,000 miles that we put on the trailer. So this is the first time I've actually flown to something for any ballooning experience. So I've driven 12,000 miles and seen lots of the country. So if you want to hear a lot of stories about dragging a trailer behind a van and all the way to Socorro, New Mexico, Taylor University in Indiana, and Ocean City, Maryland in 2025 during the major snowstorm that was chasing us the entire time, I've got some stories to tell. So anyhow, for what? I'm actually on the side wall here. The space opened up over here after the fact, but I'm actually around the corner. So anyhow, that's me. With that, feel free to start talking to us for posters. We'll be at our posters and talk to us. And so looking forward to seeing you all. Those of you that are presenting at the same time as me, I'll try to get out there as I can. But anyhow, so let's go ahead and do this. And then I'm sure we'll have some announcements postscript, and I have some more announcements as well too. But anyhow, let's get going. So, cool.
Okay. If we can, we are at the 11:30. According to our schedule, we're going to sort of wind some stuff down. There's a few announcements I want to go ahead and make and sort of at least talk about a couple of things here. The first thing, I'm just going to point this out. If I can. So this is one of the things, but I'll do this one first. So, actually, that's not the right one. That's the right one. Here we go. Again, I had some people, and I've already had a few people, thank you, that have volunteered for some stuff on committees. Again, if you are interested in that, there is a link here on the SBA website. It will take you to a job form, and then you can apply that, and then we'll get in touch with you guys to start setting up some of the meetings and stuff like that. Again, I really would appreciate that. I do want to make a clarification because I had someone ask me about this. No, I do not want to see Ahac end, okay? That's not my intention. I'm sorry if I scared anyone with that. Like I said, we'll do Ahac at Iowa State University, but like I said, I really need to start. I myself can't be the one organizing it from here on out. It's partially bandwidth. It's partially that I'm trying to focus on other things. Folks, I just hit level 50 back on June 20th, so I'm looking at the next chapter of things. So just a clarification. Do not want AHAC to end. I actually want it to grow even more, and I am looking for people to help me with that. So those were a couple things for sure I wanted to announce about. So just to make sure officially, again, we will hold it. It'll usually, well, let me ask the group this. I think I ask this every year. Is this time generally a good time? Okay. I know the only other thing, especially for me personally, ASEE, American Society of Engineering Education, their conference is around this time. I usually try to avoid that conference if at all possible. But other than that, I think this time tends to work for people. So I think we'll continue to shoot for that. So I will announce the dates probably in July. I'll look at my calendar and try to get that on the books right away. But it'll probably be this, what is this, the third? Yeah, this is the fourth week of June. It'll probably be the third or fourth week of June. Let's see. I do have, I've got this pretty much ready to go. This will be the survey. I will send this out both to all of the members. I'll send this out to all the attendees as well too. As I announced earlier, I want to see if we can get some information that I can pass on to the FAA for some of the information that they are asking for. I also put on here, it's optional, if you want to provide your name, organization, and email. That way I can always do some follow-ups if you want, but if you want to do it anonymously, that's your prerogative as well too. So that should be going out. I'll see if I can do that real quick before I get on the plane this afternoon. So, yes.
When you ask the question, cost per flight?
Yes.
Clarify what's the purpose of the question? In particular, is this expendable cost or the value of what's flying?
It's whatever your general costs are. I'll use ours as an example. We usually tell people our cost per flight is about $800, maybe $900. That's hydrogen, balloon, that is our travel costs. So for those costs, we're typically looking at what your launch costs are. Now, yes, if you want to include, hey, the cost of our payload craft is $1,000, $500, something like that, that's fine. What the FAA, I think, is looking for is they want to have, if they're going to impart we're going to put this requirement on it, they usually try not to exceed, I'm sure, some sort of percentage of what those costs are. So, I don't know if that.
It seems
I can collect both, right.
Therefore, it's the cost of what you're flying, not the cost of how much you spend you're flying.
No, I think what they're looking at, because they do this for other things, they're looking at what is the cost burden on that. And so they're probably trying to do a comparison with, to say if, so they did this with ADSB. They were trying to reduce the cost of what it would cost for, like in general aviation, of that hardware, so that it wasn't exceeding a certain burden to the aircraft owners for that. My guess is they're trying to do the same thing. They know they're probably going to impart some sort of requirement. They want to make sure that requirement doesn't exceed a certain percentage for that. But you're right. Whether we have like two different costs with that, right? We have a operating or launch cost, and we also have that. So why don't I'll go ahead and add an extra field. I'll clarify what is your typical launch cost and what is your value of spacecraft. So, and I lost my screen. Okay. Those were the two main items that I had, Ahac for next year. We have time. We have until noon officially. But are there any? Oh, Eric has some stuff he wants to talk about. Oh yeah. Oh, thank you, James. Yeah.
This is good. So while Matthew gets, we need to do some more prizes here. So while Matthew does this, let me give you a couple items. I'm going to try. Switch over. Yep, so I just put my email, my own personal email on this, and the reason why I'm doing this for a couple reasons, and I think Matthew knows this and he probably won't take umbrage. The Janeway system for Iowa State Digital Press is okay, but it's got some flaws. And so it might be easier for some of you at this stage to just contact me directly with your revised manuscripts and such, especially for those of you that have manuscripts. To just send that to me directly and I can just deal with it that way. We're not that large of a group of folks, so just kind of deal with me directly, send me your file manuscripts. You will probably still get, those of you that are waiting on reviews yet, and I mentioned this on day one, you'll still probably get some stuff from the system, so do pay attention to that as well too, for feedback, but do pay attention to that, get those revisions in. My life is not going to be my own once I start fall semester, so I really want this done. I want the manuscripts hopefully wrapped up before fall term for us starts on the 24th of August. So I really want conference stuff done with in my rearview mirror before that's done. So if you submitted to JHAB, again, I'm going to hopefully try to shoot to get that done with and reviews for that as soon as possible. Thank you. Some of you have already reached out as far as helping me with reviews. Faculty, you know who you are. Please, if you haven't reached out to me yet, please reach out to me. I still need help for reviewing, still even conference proceedings and also JHAB. I cannot, it can't be this is partly what Matthew's talking about too. It's not legitimate if I wind up being reviewing for some people. It's not fair. I've got conflict of interest with a couple of other folks, technically maybe, for that. So just please reach out to me. So there's my contact information. I'm also, I believe, on the website, but if I'm not, let's also provide that. And I'm at St. Catherine University. Some other things. So just because I'm going to do this, because I did this last year, so this is a little bit early. We're going to do some giveaways, but let me just kind of do the following, because I think one of the things that I have realized at my institution is that this doesn't happen enough. So I'm going to take the next couple minutes to sort of thank some folks. So starting with Matthew, let's thank Matthew for president of SBA here. So let's thank Matthew. Also on the board in the front row, Dr. James Flatten here. So let's thank James for all the work he's been doing here too. And also, certainly last but not least, let's thank Bill Brown here for hosting and for all the work that you've done here. Bill, it's been awesome. And the Space Hardware Club. Thank you guys. It's been a really, really good time. Thank the audio folks in the back, so thank them too. So appreciate y'all. And faculty, if you want to applaud your students, they've done a great job. So students, and vice versa, students for your faculty mentors. All right, we can't do it without you. I always say that this group is always part of collaborative undergrad research, CUR. If you want to learn more about collaborative undergrad research, I'm also part of that group as well too, and I see that our organization is really a part of CUR, collaborative undergrad research, because we really are trying to strive for undergrads for you to be able to present, get your stuff published. So if you want to learn more about CUR and what we're involved more nationally in that too, please let me know. So with that, thank you all. It's been my pleasure. So helping you all out and get stuff published, and again, I'll do what I can. So with that, I think Matthew, it's your turn to. Oh.
Yes, and thank you, Eric, of course, for everything, especially handling all the conference papers and, again, with the journal and stuff like that. Bill has another announcement that he wants to make real quick. So.
Okay, for those who are attending the 88 buffet, right next door in that same strip mall with the Chinese buffet is a marvelous ham radio store called Gigaparts. And they have 3D printing, they have telescopes, and a big ham radio section. So for those of you, after we eat lunch at 88 Buffet, who would like to go and see what they've got there, I'm planning to go there right after we eat, and you all are welcome to come with me. And I'll point out some of the things you might need for things like HF Whisper and the antennas you might need, and that would be the place to get it. So we are blessed to have one of the largest ham radio stores in the country right here in Huntsville, right next to the Chinese buffet. So, and I wanted to have a very special thanks to the Space Hardware Club members for their incredible work that they put in. They put on hours and hours and hours arranging all the details for this conference. And it's been a pleasure to work with you, and thank you so much for all the efforts. It would have not been possible for this conference if it weren't for their efforts. Thank you.
Yeah, and again, thank you to the Space Hardware Club for everything. And Bill, my wife may hate you for telling me where Gigaparts is. We'll see how much I can stuff into the luggage. Anyways, yeah, that might be a mistake. So let's go ahead and give away some stuff, and then we'll see if we want any other topics we can talk about that, but let's give away some stuff. So I swear I'm using random.org. So this is another one for one of the Space Hardware Club. Brooke, is Brooke here? Oh, okay. Yeah, let's do that. And for the Space Hardware Club, we'll yeah, so. Okay, let me roll another number here. 28. Tony Well. Is Tony? Okay. Okay. We'll do that. Let's see. Hopefully we can get a couple that are still here. 18. Let's see. That would put us University of New Orleans, Arnab. There you go. And okay. No, that would be me. That's not fair. I can order these whenever I want. Let's see. Oh, random number generator, you're failing me. There we go. Let's see. Missouri University of Science and Technology, Mohanat? Yeah. There you go. All righty. Good. Now, and by the way, I think there is still a few stickers and stuff, so I will put these out back. Again, feel free to take those. Again, I am not taking this box home, so it's either that or the Space Hardware Club's going to get a bunch of stickers as well. So there you go. I actually sold American. Okay, Eric, you said you want to announce something?
Good suggestion. So, before folks go, I think it'd be cool because we usually have done this on the steps of St.
picture.
Kitts and stuff, but we're not at St. Kitts this year. So, we've got the wonderful UAH logo back of us. So maybe if folks want to line up in front here and we get a group photo. Folks that want, again, if you don't want to be included on a photo that could go up online, we don't have a waiver, but if you're standing in front, you're a waiver. Here we go. And we'll try to get somebody that's got a camera that can do it for us. You can? You got me?
On the far side.
I'm not getting on my knees. That's ridiculous.
Left yesterday.
With that, is there any other topics or anything that you guys want to discuss? We do. Yes.
Thank you everyone for your thanks earlier, and go to GigaParks. We love GigaParks here at the Space Hardware Club. We go there all the time for fun.
Hey, we're even able to like order from them, and if somebody will like go over, use a school credit card and buy things there, it's great.
So we're gonna try to go get that balloon back, so we won't actually be at the dinner or GigaParks. It's gonna be like 3 hours, but we appreciate the week, and thank you all for being welcoming and kind.
Very good. Thank you. Any other last minute announcements? Oh, name badges. Honestly, with these name badges, you can keep them if you want. Again, I think for next year I'm going to get a whole new set. So yeah, go ahead and keep the name badges. You don't have to worry about those. Any other announcements, last minute, go backs, topics? If not, once again, thank you to all of you. I greatly appreciate all of the support and everything you guys have done. I really hope we'll see you guys in Iowa next year. Be on the lookout for more emails, and have a great rest of the summer.